In our last video, we met our substitution rule, that through the substitution, x equals g of uv, y equals h of uv. And by being able to compute the Jacobian, we can convert an integral from being in terms of x and y to being in terms of two new variables, which here in the formula are called u and v, but can actually be whatever we'd like. And we've actually already seen this because the formulas are x equals r cosine theta and y equals r sine theta. Right, they convert from a polar region back to a rectangular region, or we can think of the substitution as converting a rectangular integral to a polar integral. So I want to calculate the Jacobian for this substitution. So this will be a j of r comma theta. And then this is a matrix of partial derivatives, the partial of x with respect to r, partial of x with respect to theta, the partial of y with respect to r, and the partial of y with respect to theta. Okay, well, partial of x with respect to r would be cosine theta. The partial of x with respect to theta would be minus r sine theta. The partial of y with respect to r sine theta. And here we have r cosine theta when we take the partial of y with respect to theta. We can compute this determinant. I get r cosine squared. And here I'd get minus a minus, so plus r sine squared theta, and that is just r. Okay, well, that tells me that I can take my rectangular integral and through our substitution, replace x with r cosine theta. Just imagine converting the integrand from rectangular to polar coordinates, and r sine theta, times the absolute value of the Jacobian. Well, for us, r was positive, so I can just write r dr d theta. Hey, r dr d theta, that's that dA from polar coordinates. So our method of calculating the Jacobian matches what we said before, and now we see again that we can translate using this substitution from a rectangular region to a polar region, and our dx dy becomes an r dr d theta.